The Moon, our nearest neighbour and one of the brightest astrophysical elements in the night sky, has been circling our world since the beginning of time. But where and how exactly did it come into existence? Let's find out. The Moon is often described as orbiting the Earth, but in the real sense of things, both spatial bodies actually orbit each other around a common centre of mass. This mysterious spot, called the barycenter, is located about 4,700 kilometres inside Earth. Currently, both the Moon and Earth orbit the barycenter in around 27.3 days. This is described as the sidereal revolution period of the Moon, or sidereal month. Generally, the Moon has and displays 8 phases, including new, waxing crescent, first quarter, waxing gibbous, full, waning gibbous, last quarter, and waning crescent. All of these different phases affect how the Moon appears on Earth. For instance, the new moon happens when the Moon is sandwiched between the Earth and the Sun. During this period, Earthlings can only view the side of the Moon that is in shadow. The next phase, called the full moon, occurs when the Moon is directly on the opposite side of the Earth and the satellite's illuminated side is beamed to Earth in its full glory. Notably, the whole system of the Moon and our Earth rotate about the Sun once per year. Hence, the angle of brightness changes by around 1 degree every day. Due to this phenomenon, the timing between one full moon and the next is estimated to be around 29.5 days. Astronomers call this the synodic month, or synodic revolution period of the Moon. The average temperature on the Moon is about 127 degrees Celsius when the Sun is at its peak. However, it drops to around minus 183 degrees Celsius when it's dark. Furthermore, half of the Moon is illuminated when it is placed at a right angle to the Sun. This occurrence is described as the first and last quarters. As for the waxing and waning crescent phases, they are formed when 1/4 of the Moon is lit up. Meanwhile, we only get to view the waxing and waning gibbous phases when around 3/4 of the Moon is illuminated. Ironically, when viewed from the Moon, our Earth displays all of these phases, but only in the opposite order. The rotation of the Moon helps to regulate the length of the Earth's days, among many other things, which we'll talk about. But before we do that, let's walk you through the Moon's origins first. There are quite a few theories that explain the formation of the Moon. Perhaps the most widely accepted of them all is the giant impact hypothesis. The giant impact hypothesis postulates that the Moon was formed when a large object collided with Earth at neck-breaking speed some hundreds of millions of years ago. The early days of the universe were quite chaotic, starting with the Big Bang, the violent explosion that led to our universe and everything within it. During these wild times, there were a lot of collisions and explosions going on. Most times the process led to the formation of different celestial bodies. But there were times when the process didn't complete its full course, meaning some objects and bodies weren't able to make it to full planetary status. It is believed that one of these premature celestial objects rammed into Earth with an enormous force that produced 100 million times more energy than the event that led to the extinction of the dinosaurs. The impact of two massive bodies colliding with such remarkable force and energy left a huge chunk of debris behind in space. Consequently, gravity bound the debris together, and that's how the Moon came to be. After decades of scientific studies, scientists have identified the tyrant that bumped into Earth as Theia, a rogue space object about the size of Mars. Based on the current composition of the Moon, Theia would most likely have been made up of light elements. The giant impact hypothesis predicts that more than 60% of our Moon is made up of material from Theia. However, the rock samples obtained from the Apollo missions suggest otherwise. As a result, the Earth and Moon are made up of the same components, more like twin planetary bodies. Another hypothesis that explains the formation of the Moon is the co-formation theory. This theory posts that gravity most likely caused materials in the early solar system to bind together at the same time that gravity bound particles together to form Earth. This theory corroborates the giant impact hypothesis. More recently, in 2012, Robin Canup, a researcher at the Southern Research Institute in Texas, posted that our Earth and the Moon were formed at about the same time, when two objects about 5 times the size of Mars collided. After colliding, the two similar-sized bodies then re-collided, forming an early Earth surrounded by a disk of material that combined to form the Moon, NASA said in a statement. The re-collision and subsequent merger left the two bodies with the similar chemical compositions seen today. The last thesis, called capture theory, suggests that the Earth's gravitational force pulled in a massive body into its orbit. Usually this is the process by which other moons in our solar system are formed. This includes even the Phobos and Deimos moons of the Martian world. The capture theory explains the difference in the composition of Earth and its moon. But these types of orbiters are quite oddly shaped, instead of being spherical bodies like our moon. But unlike typical moons, their paths don't align with the elliptic path of their parent planet. However, the giant impact hypothesis remains the best model for explaining the origin of our moon. Other than the International Space Station, the Moon is the only place outside Earth where humans have set foot. Official measurements show that the Moon has a radius that stretches across 1,740 kilometers, which is equivalent to a third of the width of the Earth. For perspective, if the Earth were the size of a nickel, our Moon would be as big as a coffee bean. On average, the Moon is about 384,400 kilometers away from our planet. The Moon has an interesting shape. It is slightly flattened in a weird way, such that it bulges a little with respect to our Earth. This skewed shape means the Moon's mass is not uniform. For instance, the center of mass is displaced by about 2 kilometers towards our planet in relation to the center of the kinematic sphere. At the same time, it features surface concentrations known as mass. These mass are responsible for causing the Moon's gravitational field to increase over local areas. But quite remarkably, the Moon doesn't have a global magnetic field like our Earth does. However, some areas of its surface experience permanent magnetism, which suggests that some magnetic activity might have gone down on the lunar surface in the past. The Moon has a thin atmosphere, too thin to protect its surface from the steady barrage of asteroids, meteoroids, and comets. And this is why the lunar surface is filled with craters of different sizes. The Tycho crater, for instance, is more than 85 kilometers wide. The Moon is critically important to maintaining the balance of the life cycle on Earth. According to experts, the impact of the Moon's gravity combined with that of the Sun causes the Earth to move back and forth like a tug of war. Consequently, this movement is responsible for the tides of the oceans on Earth. Scientists suggest that these tides could be responsible for pushing minerals and chemicals into the oceans that formed and sustained the primordial soup, which led to the origin of life itself. Furthermore, the influence of the Moon on the Earth helps to slow down the Earth's rotation. Without this, the Earth would rotate faster than it currently does. In other words, without the Moon's influence on the Earth, a typical day would be reduced by many hours. In fact, several hundreds of millions of years ago, a typical day on Earth was a lot shorter, about 6 to 8 hours. It is safe to say we have the Moon to thank for the stability of our Earth, and hopefully we don't lose that stability anytime soon.